had angioedema with an ACE or ARM. The most serious side effects are angioedema, low blood on. And welcome everybody to our Friday Plain Talk, brought to you by Pro 15, representing the northeastern part of the state and advocating for our economic future. Plain Talk is also brought to you by Colorado REA, and we thank them for their sponsorship. Today we are having a topic on greenhouse gases, carbon sequestrations, a lot of new bills and a lot of new interest in this, but not a lot of people know what all of that is that they're talking about. And so our speaker today is going to give us not so much opinions as factual things. What is it? What does it do? And maybe that will help us as we look towards the future. So our speaker today is Ron Stites. Ron is the founder and executive director of the Colorado Center for Innovation in Community Capital. He is a member of Pro 15. He has a bachelor's degree in chemistry from the University of Kansas and an MBA in finance and accounting from Regis University in Denver. He has served as a high-level technical manager for multiple technology-driven companies, and several of those assignments were in the environmental field, where he was exposed to broad knowledge of greenhouse gases and their impact on climate change. And he'll be using this experience as a basis for the topic. And with that, I will turn it over to Ron. Welcome, Ron.
Thanks, Kathy. I'm going to start sharing my screen and try to get this back up, and hopefully the technology gremlins will cooperate.
Working so far.
Okay, you should have a slide that says understanding carbon footprint.
Yes.
Like Kathy was saying, I'm going to try to stick to the facts that are known and also talk about some of the things we don't really know. So give you a broad spectrum view of what is the issue. I'll try not to give too many opinions, but it's impossible not let your opinion about some things slip through. So forgive me if they do. A little bit about me. Let me add just a couple of things. I've got patents in the area of chemical processes. I've actually worked on carbon capture. I'm actually working on a project now on carbon capture. Those are some of the things I wanted to add to it, what Kathy said. I did a lot of startup work, and that's what kind of got me into this capitalization business for small businesses. And that's what we're launching with the Colorado Center for Innovation and Community Capital. That focuses on government programs. We have another company that we're working to get launched, and it's more on a private programs, small capital acquisition. I want to talk about the jargon and some of the science and some of the street science. Melanie, you have a question?
Yes, sir, not to get us too far off, but what is, you say you have a patent in carbon capture. Can you explain to me just briefly what carbon capture would mean?
That's what we're going over.
Okay.
Yeah. Okay. That's a real good question. That's a real good question, Melanie, because we do have a lot of confusion about what carbon is and carbon capture. That's what I'm trying to really explain here. And so I've actually worked on how do you reduce things like carbon footprint, and we're going to talk about what in the heck does that mean. So that's kind of the whole point. So.
And I didn't mention earlier, but if you do have questions, we'll have a Q&A at the end, or you can throw them into the chat room and we'll try to make sure we get them all answered. Thanks.
Yeah, I think this is going to take about a half hour, so I think we'll have time to talk. So we're going to talk about the jargon, the science, and sort of the street science, and they don't always align. The whole discussion started with the notion of greenhouse gases, that greenhouse gas effect. We're going to talk about that. What is that? How does it work? So we kind of understand that. The early focus was on carbon dioxide, and you'll hear me being a chemist, I'll say things like CO2 and H2O all the time, and I try to explain those and try to keep the jargon down a little bit, but I can't help myself. So the early focus was on carbon dioxide as a greenhouse gas. That goes way back, even into the late 1600s. People were starting to think about it. Then they realized that other carbon-containing compounds also contributed to greenhouse gas effect. So it kind of broadened the spectrum or beyond just carbon dioxide. That's the genesis of the term carbon footprint. It's CO2 and other carbon-containing compounds that get into the atmosphere that tend to create a greenhouse gas effect. And how much carbon you are responsible for putting into the air, that's kind of your carbon footprint. Again, those kind of street terms that come along. Then we have learned recently, more recently, there's a lot of non-carbon compound that you have to pay attention to. So we're kind of drifting back to the idea of a total greenhouse gas issue. So the terminology kind of gets fuzzy, and that's what we're trying to sort out here. So you know, when someone says something, what are they talking about? So let's look deeper into this. What is the greenhouse effect? There's a lot of molecules that absorb infrared radiation, and that's heat. When you stand in front of a campfire and you get warm on one side and you're cold on the back side, it's because the infrared radiation from the fire is warming your front, and your backside is actually emitting infrared radiation. You're losing heat. That's what we're talking about here in a greenhouse gas effect. These compounds, and they are not nitrogen and oxygen, which makes up almost 100% of the atmosphere. The things we're talking about are low concentrations of gases. Nitrogen is almost 80% of the atmosphere, and oxygen is about 20% of the atmosphere, and they don't absorb infrared radiation, so they don't get involved in the greenhouse gas effect. Other things do. At night, the Earth cools, like your backside cools, by emitting infrared radiation. These infrared absorbing gases trap that infrared radiation and hold it back into the Earth. That's what the greenhouse effect is. It's like a greenhouse, only that's not a very good analogy. Greenhouses don't really work like that, but they do tend to trap heat. That's the point. Scientists noticed that the planet Venus had very high CO2 content, about 96% back in the 1940s, and they began to sort of put two and two together. Well, Venus looks like it's very, very hot. Maybe that high CO2 is a piece of the problem. They actually did some experiments back in the, actually it was in the 60s. I'm gonna try to, got this, yeah, that'll help. The little ribbon was getting in my way. They did experiments on CO2 in laboratories to see if that greenhouse gas effect really made any difference. And they were able to actually demonstrate that it really does have an effect. CO2 does tend to trap infrared radiation against an object. Then they started doing glacial ice studies showing that CO2 content has increased since 1800 pretty dramatically, causing people to think about maybe CO2 is going to create global warming. So that's another piece of jargon. CO2 and global warming, that was the early way people talked about it. It's a little more sophisticated now as people realize more about what's going on. So people then discovered methane. chemists pointed out that there are a lot of other gases that absorb infrared radiation that also exist in the atmosphere at low concentrations. It turns out that methane is a much stronger, molecule by molecule, is a much stronger greenhouse effect, has a much stronger greenhouse effect than CO2, but it's a low concentration. It's only by molecule, methane has more infrared absorbing properties, but it's in parts per million, hundreds of parts per million, and CO2 is in many hundreds of parts per million. Most organic compounds that contain carbon absorb infrared radiation, and so most organic compounds, if they're a gas in the atmosphere, can contribute to global warming. No, can contribute to the greenhouse gas effect. Whether or not they actually do any shifting, it's interesting. That caused the whole discussion to shift to carbon footprint and carbon capture. Trapping molecules like CO2 and like methane, but also other carbon-containing compounds, trapping them and keeping them from getting into the atmosphere. And your total, the total amount of carbon-containing materials, gases, that you leak into the atmosphere, either directly or indirectly, that's what people are talking about when they say carbon footprint. And it's not just your plant, not just your operation, but even the products that you're producing, if they later create carbon compound emissions, that's considered part of your carbon footprint if you're trying to get a total picture of carbon footprint impact. There's other molecules like nitrous oxide, fluorine containing compounds, and especially water that have been shown to be stronger molecule by molecule than CO2. Turns out water is a big player because it's in the atmosphere, sometimes up to a few percent of humidity. And it is a big player in the whole idea. As you learn more about all the different interacting pieces, water turns out to be a big piece of the pie. Although people talk and keep a focus on CO2, other gases, especially methane, and to a lesser extent water, are included in the discussion. Don't ever forget about the role of water, and we'll talk about that more. The best science now includes the sum of all these in any serious discussion about greenhouse gas effect. And it also includes the practicalities of what can you affect, what can you change, and what is really outside of your control. That's the best discussions these days. What is CO2 and why do we have it? CO2 has been around for billions of years. About 3 billion years ago, in the very first, very different atmosphere Earth had, there was a significant amount of CO2. In the earliest of Earth, you had mostly coalescing elements like carbon, nitrogen, oxygen from stellar gas and dust. They eventually coalesced in the cooling planet, and you started getting solidification of stuff. And the free carbon and oxygen reacted to make CO2. So it comes from the very primordial times, the load of CO2 we have on the planet. Then later along comes water, and water reacts a lot with CO2. It's a very complicating piece of the whole puzzle. CO2 plus water plus metals, like whether it be sodium, potassium, iron especially, make carbonate minerals and rocks, making the solid part of our planet as we know it. The Earth remained very hot, and the geological heat trapped inside the core, when it came into contact with carbonate and silicate rocks, it would release the CO2 in volcanism. So you have these volcanic episodes causing CO2 to go up, and we have other mechanisms causing CO2 to go down. So first we had the water comes and pulls a lot of CO2 out of the air, reactions with metals to make rocks. Then you have heat and volcanism pushing the CO2 back up into the air. So you're already starting to get this back and forth of high levels of CO2, low levels of CO2. At one point, the atmosphere was roughly, could have been as much as 40% CO2 and nitrogen probably being the rest of it. All dissolved in that liquid water in the oceans. And then marine photosynthesis took over. Oxygen plus CO2 started with photosynthesis around 2.5 billion years ago. So CO2 plus water plus light energy makes carbohydrates of all kinds, plant materials, flesh, everything else, and oxygen. So you started getting oxygen going into the atmosphere, replacing the CO2. So now another cycle is starting to occur. The photosynthesis caused an atmospheric oxygen explosion starting about 1 billion years ago. Initially, all the oxygen made also reacted with metals and rocks and created other oxygen containing minerals and eventually got into the atmosphere. CO2 and oxygen have sort of teeter-tottered back and forth since that time, up and down like a yo-yo over long periods of time. High temperatures throughout this whole time, the evidence we have is that when you get high levels of CO2 in the atmosphere, we also have high temperatures on the planet, high average temperatures. And that evidence is fairly strong, seems like pretty good correlation. Not so sure about all the causality, but the correlation looks to be pretty strong. So what's methane? Methane, the other major carbon-containing gas we really concern ourselves with, that's been in the atmosphere forever and ever. It also comes from stellar gas. You see methane out in space. We can actually see it out there in stellar gas clouds. So we had methane in the beginning, and it could have been several percent early on. Eventually, though, once oxygen comes along, oxygen plus methane plus some light energy to ignite it, and doesn't really burn. It actually is a slower reaction in the atmosphere, upper atmosphere, not a flame, makes water and energy. And that's, of course, what we use in the natural gas industry to make energy, is we take natural gas, mostly methane, and burn it with oxygen to make heat. Well, that same reaction caused the methane content to drop dramatically and caused some cooling of the atmosphere. And now we have maybe 100 ppm or so of methane. Atmospheric methane has gone up and down. Oxygen makes it go down, and generally it's around double handful of ppms. In fact, methane has a lower lifetime. It actually reacts with oxygen fairly quickly, and an average molecule of methane, half of them will be oxidized in about 12 years. CO2, once it gets in the atmosphere, hangs around longer than that. Another source of methane causing methane to go up is any kind of incomplete combustion, like a forest fire or a grass fire, not only makes CO2, but also makes methane. So too, any poor combustion of fossil fuels will generally make methane. Another big source is biodegradation of plants and animal material. The latest kind of craze right now is talking about livestock based methane. It's really minor compared to anything like bogs and wetlands, landfills, and even young fossil fuel deposits that are still outgassing methane. Young coal deposits, yeah, but that's the big one. Bogs and wetlands also. So that anaerobic biodegradation of materials out there in nature are a pretty significant source of methane getting into the atmosphere. Whenever you burn natural gas, especially in internal combustion, you have slip. Some of the methane doesn't burn. That actually goes into the atmosphere. And of course, any leaks that you have in production of natural gas can be a significant source of new methane going into the atmosphere. Methane on a molecule by molecule basis is about 30 times more powerful than CO2, but based on the current concentrations and the way everything works together, it only has about 1/8 the impact of CO2. So it's the lesser of the issues, but it still could be an issue. What about water? We need to talk about water to really understand the greenhouse gas effect. We have these huge deposits of water called oceans. Water in the atmosphere as water vapor is a very powerful greenhouse gas, not just from infrared absorption, although it's a powerful infrared absorber. You also have a phase change. When it condenses into clouds or into rain, it's absorbing heat. When it evaporates, it's losing heat. Sorry, the other way around. When it's evaporating, it's gaining heat. When it's condensing, it's giving off heat and keeping things warmer. It's about 60% of the current greenhouse gas effect based on its ability to interact with the heat cycle and its concentration in the atmosphere. It's the bigger piece of the whole pie, even bigger than CO2. Interestingly, higher temperatures, if the Earth warms, more water evaporates and gets into the atmosphere. We have a wetter climate and more storm activity. But we also now have more CO2, more water in the air, and it actually causes more greenhouse gas effect. You can see that it begins to start cycling toward higher temperature. Once you trigger heating somehow, water can help contribute to heating more. The oceans that have absorbed the CO2 out of the atmosphere, they hold CO2 better if they're cold. Cold water holds CO2 better than hot water. Just warm up a can of soda and open it up, and you'll see that a lot more CO2 comes out than if you have a cold can of soda. Heating releases CO2 from the oceans. So if you start this cycle of warming, you're going to get more water vapor in the air and more CO2 out of the oceans in the air. So there's pretty good reason to believe that you could start a runaway cycle. Higher temperatures means more CO2 from the oceans. Water and CO2, the way water interacts with CO2, can create a major shift in temperature and maybe the way that events trigger major changes. Dropping temperature can run the other way. If you start dropping water out of the atmosphere, you'll tend to start cooling everything off and pulling CO2 out of the air. So there's kind of this unstable settling that we have had. And these charts, I've tried to align them based on time. This shows from a 1 billion years ago, when we first started really seeing some oxygen in the atmosphere, what we think the oxygen content has been from over the last 1 billion years. these blue areas are actually ice ages. And we are just coming out of an ice age that probably ended around 11,000 years ago. So this cycle of heat, cold, ice, palm trees has gone on quite a lot over the millennia. These two graphs down here show the CO2 concentration and the average temperature. And here we have an ice age where we had CO2 goes down, temperatures go down. At the time, photosynthesis has been really sucking all the CO2 out of the atmosphere, creating an ice age. Then you have this crash of temperature, and then something happened, and we're not sure what. Some event probably occurred that started the cycle going back the other way and created a warm period. And now from here onward, these don't align because they're on different scales. Over the last basically 100 million years, we have been in mostly a cooling cycle, except for 50 so million years ago, we had a very warm cycle, the Eocene period right here. And we're not even sure why we had this spike. These don't align very well. Sorry, but I couldn't stretch this differently. This Eocene cycle corresponds with a spike in temperature and CO2 at the same time. Now, the data that people show these days are data in this area, which is a small fraction, a very tiny fraction of the whole history of the Earth. But even through here, even these small changes in temperature and CO2 seem to align fairly well. So since about 400 million years ago, we've seen this shift up and down of CO2, oxygen, big swings in global temperatures, and a tendency for those temperatures to follow CO2 content and make quick turns and run one direction for a while and stay there a while, and then something else happens and it makes a turn and runs the other direction for a while. So there seems to be triggering events over the history of the planet that seem to make a huge difference in where we end up. So recent history, we're talking about even the last 40,000 years now, we see some trends that are cause reason to pause. Here's the CO2 content. This is actually a very low number over the history of the Earth. It starts climbing up as if we're starting to really recover from an ice age. But then once you hit the Industrial Revolution, you end up with a big jump. And it's this big jump that scientists are saying, could this be triggering? Could this trigger a very rapid global warming trend? So that's the issue. Lots of factors come into play. So you can't be sure, but that's the question. That's the thing that causes people to pause and say, what about where are we headed? So regardless of how nutty some of the claims are around CO2, climate change, et cetera, and some of them are nutty, this is a cause for concern. That kind of a change over a short period of time is something to think about. So what do we do? Well, obviously you got to focus on the big hitters: water, CO2, and methane. Those are the ones that matter. There's not much we can do about water. It is a big player, but we really can't go around and dehydrate the atmosphere. More water in the atmosphere generally is a pretty good thing. So we can't do a whole lot with just water on that kind of a scale and level. When it comes to CO2, that's, as people think this through, it's like, well, is burning a fossil fuel the big deal? It's called anthropogenic CO2 change. There's no question that burning fossil fuel has increased atmospheric CO2. And coal is worse about that than oil or natural gas. The reason is coal is almost pure carbon, and all the energy comes from carbon plus oxygen to make CO2. Oil and natural gas contains also hydrogen, and some of the energy you get is from the hydrogen becoming water. So it's not all just making CO2. You make a mix of CO2 and water to make your energy. So coal contributes more than oil, contributes more than natural gas. The question is this the big trigger or not? And what do you do about it? Forest fires, and I keep harping on this because I just came from a meeting on forest fires. Forest fires release, and grass fires release a lot of CO2 and methane. We need to work on the forest fires for a lot of reasons, potential global warming being one of them, but that's a topic for another day and something here in Colorado we got to pay close attention to. Methane, there's not much we can do about the bogs, the wetlands, and the fossil fuels. There's no sense in getting all excited about the livestock. It's a minor issue, and there's no payout. The cost benefits just don't make any sense. So that's just one of those. I'm sorry, it's just a nutty idea. Fossil fuel production, plug the leaks. Don't just vent natural gas. Yes, it's not immediately toxic, but it's not a good thing to have in the atmosphere. And if you have to do something, you're better off to actually flare the gas and turn it into CO2 than to actually just dump methane. And then do all you can to reduce the slip or the losing of methane in any combustion process or the production of natural gas. And then, of course, one thing to do is always ditch the stupid stuff. And so how do we recognize some of the stupid stuff? How do we avoid it? Well, always look at the total solution and the total impact on those three big hitters. There's a lot of shifting around of the problem to somewhere else rather than actually fixing anything. When it comes to water, are we using water effectively? And does any model that anybody's proposing out there for global warming, does it take into account the role of water, which is big and complicated? If it doesn't take it into account, then it's probably not a very useful model, not really. The chemical interaction between water and CO2 is probably going to be the best basis of any kind of remediation strategy. Water is cheap, abundant, and reacts well with CO2, and a lot of other things don't. So if we're going to try to do anything like capturing the CO2, that would be called carbon capture, and do anything with that CO2, that process is going to involve water, not amines, not expensive metals to absorb CO2. That's all out there. There's lots of stuff proposed that just makes no sense. Look for the solutions that use water. When it comes to CO2, always look to see if the solution makes more CO2 than it actually saves. The corn ethanol non-solution is one of those. It was proposed for a long time that corn ethanol was going to be something good for CO2. It's not. It makes lots of CO2. That's why they have gigantic cryogenic tanks outside of every corn ethanol plant to take the CO2 from fermentation, capture it, and try to sell it to somebody. It's not a good CO2 play. It's got other reasons to make some sense, but not for CO2 capture. There's a lot of other things proposed that could take up a lot more energy and create more CO2 than it ever absorbs or sequesters. Work on forest fires. there's a lot of simple solutions that are not being done on forest fires, and a lot of them are just funding, politics, and some economics. The complex, expensive methods to absorb CO2 out of the atmosphere are, for the most part, really bad ideas. Methods using water and plants or microbes generally makes more sense. The photosynthesis, whether it be with algae or with plants, is probably the smartest play. There's been millions of years of research we didn't do on making photosynthesis work for low concentrations of CO2 in the atmosphere and sequestering that into cellulose, carbohydrates, etc. Those are the solutions that make sense. In fact, I'm working on one right now, trying to take CO2 out of the air in chicken houses and using it to grow algae to feed chickens. It actually might work. Methane, there's not a lot we can do other than what we talked about, being careful with it, don't waste it, burn it completely when you do burn it, but forget about the idea of livestock. Always look at the unintended consequences, engage and speak up. Renewables, the energy of the future, and maybe they always will be, I don't know. Again, look at the total solution and impact. When it comes to water, be careful that you're using so much of it that you have put pressure on a scarce resource. CO2, takes energy to make some of these things and to create some of these materials, some of these exotic materials for some of the solutions. Running the equipment, creating the chemicals and using the chemicals. Some of these things just look so energy intense. It's hard to imagine that you're coming out ahead. A little bit of CO2 that you're actually able to do something with, who knows how much CO2 you've created upstream to do all this. Same sort of thing with methane. Look at the total impact of the energy balance and the energy being consumed, the energy being traded off. You've got to look at a bigger picture, and a lot of folks don't look at those bigger pictures when they start looking at some of these ideas. Take a look at land usage. That's an important piece of the puzzle. Solar and wind are not particularly effective, efficient, and they can eat up a lot of land. Think about that. Look at the byproducts, including toxic waste. This is one of the things I've worked a lot in alternative fuels and renewables, and you would think that'd be one of the first things people look at, but they don't. They don't pay much attention to the toxic wastes that you might be creating with some of these processes. Raise those issues. And the equity of who's paying for what, whose ox is getting bored in this deal. That's a legitimate question. And then always costs versus benefits, and include replacement and maintenance costs. Stay calm when the big they scream, the time is running out. Relax. I remember I pointed to the Eocene period. It wasn't all that bad. 52 million years ago, when oil shale was being formed, CO2 concentration was between 1,000 and 2,000 parts per million. Today, it's 400. And we're starting to be concerned about, are we triggering something? And we should be concerned about that. We're not dying immediately. The oxygen content was fine in the Eocene period. It was nice and warm. Colorado was actually lush and green with happy forests and no dinosaurs. Of course, if we went back to the Eocene period, it'd be a different story for New York City or any coastal city, because there was no ice, ocean levels were higher. So, okay, there's some downside to going back to that. It's a little bit tongue in cheek, but don't be stampeded into wasting money on self-serving, stupid stuff. That I've seen that. There've been multiple cycles in the environmental business just like that. Wrapping up, what's my suggestion? Engage. Continue to educate yourself and keep an open mind about what is happening. The science is pretty good, but it's not perfect. And what you hear on the street is usually an extrapolation beyond reality of one idea here or there. Don't let yourself get trapped into any political narrative or camp. Don't buy the simple solution. That's probably a con. This is a complicated issue that needs a lot of thought and a lot of study, and it needs action, but it needs smart action, considered action, not knee-jerk reaction. And also remember, we run this country, not the they. So I'm ready for questions. I hope that helps.
Okay, I'm going to ask the first question.
Okay.
In the 80s, they told us all to stop using hairspray
Yep.
because we were putting a hole in the ozone level.
Yep.
What's the ozone level? Is that CO2?
No, those are fluorocarbons.
So it's
Yeah.
another thing.
That's another thing. And it was a real thing. It was a real thing. We've pretty much done what we can do about that. We've basically taken the fluorocarbons out of things like propellants that you just blow off into the atmosphere. And we're doing a much better job in controlling the freons that are in refrigeration systems. So for better or for worse, we've pretty much done what we can do, at least in the Western, in the Western civilization, Europe and the United States, about all we can do. There's other folks that haven't done all they should do, but we've done about all we can do.
Well, I'm not sure whether I have more questions than I had before, but I do think that I understand it a little bit better. I at least have a clue, and I love the timeline coming up to where we are at now. So I learned a lot, and I still got a lot more to learn. It's probably not anything that any one of us are going to ever fully understand, which was not what we were trying to attempt here,
Right.
but more to have people know the terms and kind of have an idea of what went on those. So Melanie, you had questions early on. Were those questions answered for you?
Yeah, the question that I had was answered. Thank you very much. I thought it was a great presentation. I think what I've known in my heart is what you were presenting today, which is what we have seen and what I learned back in early science is what we're seeing here. And what I know of my life is everything is cyclical. And it appears to me that as we come out of an ice age, we go into another age. And what we do with our planet is important. But as you said, it's not a knee-jerk reaction that we should have. It's not something that we should run around and react to one small group of people saying do this, or one small group of people saying do this. We should have a really thoughtful reaction that is based on really good fact and what we individually look at and balance with what really matters in our lives. And that's what I'm going to take away from your presentation.
Yeah, thank you. That's really kind of my point is this is pretty complicated. And there are people out there taking one idea and running with it, often self-serving, frankly. But there are other people that don't they just want to turn a blind eye to what's going on, and that's not smart either. Their CO2 concentration is going up, and it could trigger something if we aren't careful, if we aren't thoughtful, pay attention.
Okay, before we wrap this up for another day, is there anything, any other questions or last minute comments? Well, Ron, thank you very much. I appreciate it. For everyone else, this will be up on our YouTube channel, on our Facebook page within the next hour or so, so that if you miss parts of it, you can watch it again. Share it freely. Let's get the information out there. Again, thanks to Colorado REA for being a sponsor of our Plain Talk. And everyone have an absolutely awesome weekend, and we will see you later.